Your introduction, and I'd like to greet all friends at the Thomistic Institute. Many good friends there. Thomas Davenport, I guess he will be there, or at least he will follow the talk. And I feel very lucky because I have the opportunity to talk about one of my favorite topics, about science and religion, but from the point of view of physics. And so let me share my screen. So this is the PowerPoint that I would like to follow. And so the idea, let me go directly to the outline of my talk. So before I explain the different parts of my talk, I would like to explain to you why I have decided to talk about this science and religion dialogue from the point of view of physics, and why I think that we actually live in an exceptional universe. So there's one reason. The first reason is that my impression is that this dialogue of science and religion has developed mainly in the field of biology, perhaps because of the question of evolution. So usually when you speak with a believer about science and religion, so the usual topic is evolution and religion, the compatibility of evolution with God's action in the world. But there's a second reason why I'm interested in physics. And the reason is because I think that when we initiate the dialogue with a scientist, as a believer, so I have the impression that if we underscore too much God's transcendence, maybe this is a non-starter for the scientist, because he thinks, okay, yeah, of course, well, the origin of being and all that, but you know, in science, I'm working with things that already exist, so I don't care too much about the origin of being. But on the other hand, if we underscore too much God's action, it could seem that we are talking about the God of the gaps, so that we turn to God whenever we find some problem in our scientific explanations. There's some gap in the explanation, and then we try to fill the gap with God's action. So I think this is the Sheila and Charybdis of this dialogue, and I think that we should be able to find some clue in nature, at least in nature as studied by physics, that point towards this transcendent God that is also a personal God that is involved in creation from the very beginning, and because of that is also immanent in nature. So as you may see, I want to talk about these four things. I will talk about two mainly ontological issues: the question of the singularity of our universe from the thermodynamic point of view. I will also speak about the emergence of systems, complex systems. I think these two issues are mainly ontological. And then I would like to shift to a more sort of epistemic issues that have to do with the intrinsic duality of our most fundamental theory of nature, quantum mechanics, at least from the point of view of physics always. And also the question of naturalizing information, whether is it possible or not to naturalize information. That's a huge topic, a controversial topic, and now information is one of the key concepts in this field of philosophy of nature, and also in the dialogue between science and religion. And well, in the end, I'll try to give you my own view, how I think that the emergence of immaterial knowledge, of intellectual knowledge, in the case of human beings, is the apex in nature, in a nature that evolves itself. Okay, so let me start with the first part of my talk, the thermodynamic singularity of the universe in which we live. So I'll try not to be too technical, but I have to say some things just to introduce the problem. And now in physics, we usually think in terms of degrees of freedom. Now just think how many degrees of freedom do we need to describe a particle? Well, 6. We need 3 degrees of freedom for its position, and 3 degrees of freedom for its momentum, for its velocity. Now imagine that our universe is composed by n particles, so I need 6n degrees of freedom to describe a specific microstate of my universe. So I can describe that in a abstract space that is called the phase space, that should have 6n dimensions, and each point in this phase space represents a specific microscopic state of the universe. Now, so I can make a partition of this phase space of the universe. And now in this partition, so the microstates that are in the same box are related in the following sense. So of course they are distinguishable from the microscopic point of view, but they are indistinguishable from the macroscopic point of view. Just think, for instance, of a gas, of a very simple gas that I can describe macroscopically, referring to its pressure and its volume or its temperature. But these macroscopic magnitudes are compatible with many different microscopic configurations. So now with this idea in mind, we may understand the value of the definition of entropy that was introduced in the famous Boltzmann formula for entropy. So the entropy S is proportional to the logarithm, for technical reasons, of the volume of the phase space that is shared by all these macroscopic states that are compatible with one single macrostate. Now, so the idea is that, well, of course, if one macrostate is compatible with many possible microstates, then I will have a huge entropy. So the idea of huge entropy is that many different microscopic detailed states of the universe are compatible with a single macrostate. Now, let me move on and talk about the second law, the famous second law of the thermodynamics, the law of increasing entropy. So the second law says this, that the entropy is a non-decreasing function of time in a closed system. And now if we apply this to the universe, so the entropy of the universe would be a non-decreasing function of time. So the entropy of the universe is always increasing. Now, again, think about the phase space of the universe. And now if we just think statistically, so the likeliest possibility for our specific state in the universe would be to remain in this partition that is, well, the huge partition with that contains the hugest number of microstates. So this would be the state of equilibrium of the universe, of course. But the point is that we are not in this position now. So now corresponds to this situation. So we live in a macrostate that corresponds to a moderate entropy. It's at a moderately low entropy. Now, what's the evolution of the universe? Remember that each point here in this phase space represents a state of the universe. Now the evolution, if we think in statistical terms, so one would think that so the likeliest evolution would be one in which we go to partitions where entropy is increasing. So that's the rationale behind the second law. And of course, the second law is saying that, so the entropy is increasing. But if we move backwards in time, if we think what would happen backwards in time, so if entropy were just a statistical question, since the fundamental laws of physics do not distinguish between past and future, so you can change t and minus t and you would obtain the same laws. Just think about the second law of motion of Newton. So acceleration is a second derivative of time. So time can be changed to minus t, to minus time. Then if we were talking only of statistical reasons, so the situation should be that we come from also a part of the universe with a huge entropy. So this going backwards would violate the second law. And since we think that the second law is something fundamental in the universe, so the situation is not this, it's not situation C. Actually, the situation that is compatible with the second law is that we come from a situation D, where we start from a very low entropy, a very tiny entropy. So this is the past hypothesis. It is called the past hypothesis in this field of thermodynamics. And the idea is the Big Bang starts in a situation of extremely low entropy, very tiny entropy. And actually this can be estimated. There's some estimation. I must credit Roger Penrose. This is discussed in his book, The Road to Reality, and other books. But there's an estimation about the degree of specialness or speciality of the Big Bang at the very beginning of the universe. So these are the estimates. So our universe is as special as 1 part compared to 10 to the power of 10 to the power of 123. So beware, this is not 1 compared to 1 followed by 123 zeros, but 1 followed by 10 to the power of 123. So this number cannot be written down and in the actual universe. So if we had to occupy a space of 1 centimeter for each zero. So it's probably the hugest number that we can find in current science. And in Roger Penrose's words, this is the most profound mystery of cosmology. So nobody knows actually why we have such very low entropy at the beginning, at the Big Bang. It's a pictorial representation of the pain that the creator should take in order to find the right initial conditions of the degree of specialness of exceptionality of our universe at the very beginning. Well, just to finish off with this discussion about entropy. So this is a small joke. We usually tend to think of entropy in terms of disorder, that it's right, but it's not the whole story. So we have a problem with entropy, and the problem is very well described with these words, that one of the ends of the curve of evolution of the universe starts in a region of extraordinarily minimum entropy. Why? We don't have an answer for that. Why is that relevant? Well, that's relevant because it shows that our universe doesn't fit in the possible universe that we could have according to the laws of physics. The multiverse theory, in a way, tries to solve this problem, speaking of many other possible universes, and perhaps ours, the actual universe we live in, is just one of them. The problem with that explanation is that, as Liz Molin shows, another physicist, so that explanation, just invoking the multiverse, fails to explain the typicality of the universe. In other words, it's no scientific explanation, because a scientific explanation should deal with why our universe is somehow typical within the multiverse. But that's not the situation. The situation is that universe is really exceptional if one looks at the huge amount of possibilities, as this entropic number shows. And so we didn't have a good explanation for that. So let's move on, and let me talk in this second part about the emergence of complexity and individual system in the universe that somehow is also related to the question of entropy, to the tiny entropy of the Big Bang. Now, perhaps you're familiar with this picture. This is related to Simon Conway's Game of Life, Conway-Morris Game of Life. So imagine the universe is this grid, and every square represents perhaps a living system, a system that can be dead or alive. And so in different iterations, so the fate of the systems depends on very basic microscopic rules. Actually, this Game of Life works with 4 basic microscopic rules. You can see the very beautiful videos, footage in YouTube, explaining that if you introduce these 4 rules, then you can have an evolution that is really amazing. So you can have patterns, the famous gliders, that they interact among themselves, they build cities, they interbreed, they feed themselves. So the point is that the emergence of patterns, something that macroscopically seems to have its own story, its own life, actually stems from very basic rules, 4 microscopic rules that have to do with whether you keep alive or you die, depending on the number of surroundings of living systems surrounding you, whether there is overpopulation or there are no, if there are too few alive systems, then maybe you die because of starvation, and well, these basic rules. So I think this is a beautiful example of what we understand by weak emergence. Let me put you another example. This is a beautiful image generated by an algorithm with any computer can generate this image. It's related to the Mandelbrot set. And so this combination of colors and this fractal structure can be realized according to very simple rules, at least with rules that can be written down with an algorithm, and the algorithm runs in every computer, and I can obtain this image that has some beauty in itself. Now, the point is that this is the result of some microscopic rules. Now, the question is, perhaps the universe, perhaps what we see, perhaps all living systems, all the complexity that we see in the universe, from life to, I don't know, of course, the artifacts that we human beings construct, perhaps all that is just the result, is the upshot of very basic rules, the fundamental rules of physics. And that's the idea that somehow is behind the scientific reduction, and from the starting point of science, of the scientific project in the modern era. Let me give a definition. This is due to Franz Wilczek's Nobel Prize. Is the author of a theory for the quarks, the asymptotic freedom of quarks, explaining how quarks behave within the proton and nucleons. And he gives this nice definition of what we understand by reduction. A complex object has been reduced to something simpler when we can show or make plausible that the more complex thing can be analyzed into simpler parts and its behavior synthesized from the behavior of those parts. So that's the idea behind reduction. So we explain the whole, what seems to be more complex, from the behavior of smaller and smaller parts. That's the idea behind reduction. So the question is, well, if this is true and we can reduce everything and we have fundamental particles, fundamental laws of physics, and this explains everything. So when we refer to systems, living beings, to plants, to animals, in a way, this is only weak emergence, so to speak, is like different ways of speaking or referring to complex organization of particles, but it's only that. So the causal structure of what's going on is at the lowest level, the level of physics. Now the point is whether this works or not in the world as we know it. I like this picture because it's a milk drop, and it hits the ground and it rebounds. You see this beautiful crown with 24 peaks. Now it's one may wonder, or one may ask, well, 24 peaks. Could I predict those 24 peaks just from the basic degrees of freedom of this milk drop from physics and the characteristics of the floor that is hitting this milk drop? Not so sure whether I could predict that. Or maybe you're familiar with these Bénard cells. So Bénard cells are structures that emerge in a liquid when we have some threshold in a gradient of temperature. So imagine that I have here oil and it's been heated, and there is a gradient of temperature between the bottom and the top of the oil. So this heat has to be dissipated. And so the dissipation process initially starts with conduction, but there is a threshold in the gradient of temperature when conduction is not enough. Then I reach a new regime. There's a phase transition where the dissipation of heat has to be done through convection. And there's this emergence of structures, of pyramidal structure, like hexagonal structures, that are the optimal way of dissipating heat. So complexity in nature has to do with the emergence of things that apparently they are really novel, because they don't exist, these new properties, they don't exist at lower levels, at fundamental levels of nature. So when we speak about complexity, we are talking about different levels of description that are intertwined, of course, but they are different. So the microscopic and the macroscopic view. Usually we are working in a very far from equilibrium situation, for instance, in these banana cells. So there's a gradient of temperature that is responsible, or at least partly responsible, of the emergence of these structures. As you probably know, living systems are very far from equilibrium. So basically what all of us are doing, we are resisting the second law. So we are keeping our internal entropy low. So we are in order state. So to keep at bay the second law of thermodynamics and not dissolving into the universe. And when we talk about complexity, we are talking about the strong emergence. So new properties arise that simply don't exist at the bottom level or at lower levels. So the point is that it seems very, very controversial that I could explain nature just in a bottom-up fashion, just building up nature from very basic rules from physics and the fundamental particles. If we turn back to our phase space, so from the viewpoint of physics, what's going on also in the emergence of complex systems is that in this phase space, there are some attractors. So attractors are region of the phase space in which the system is usually stuck. So it spends most of its time in these special regions of phase space. So this is an attractor. So imagine that we are dealing with the weather, with climate. And so depending on the initial conditions, then I could end up with a rainy day or with a sunny day, or with more probability with a rainy day than a sunny day. Perhaps in this last picture, this is an attractor that it doesn't matter where you start from, that you will end up in this situation. So this is the final situation in which you will evolve, that you will end up with. And for instance, it would be the weather in Pamplona, so it doesn't matter how the day starts, it always ends up with rain. But the point is that it seems that life itself, the history of life, this is a beautiful representation of how life starts on Earth, and all this variation, all these new species that appear thanks to evolution, these random variations in the genome, and then natural selection. So the point is, would it have been possible to predict the emergence of life just from the fundamental particles and the fundamental interaction in physics? Or if you wish, just think about the typical interactions between the genes in a bacterium. So this is really complex, and so there is a hierarchical structure of new things that appear, and so like biomolecules and proteins and cells. So the point is, would have it been possible to predict all this from scratch? So to build nature with knowing the initial conditions and the interactions. So do we live in a deterministic universe where everything is determined from scratch, from the very beginning? So it seems quite far-fetched to say that, because it seems that we live in a universe where new degrees of freedom appear. new degrees of freedom emerge, as is the case with life, is the case with the increasing complexity that we contemplate in the universe. So let me summarize these two parts. My idea, that the take-home message is that we live in an exceptional universe because Big Bang has a really remarkable low entropy, and it is this low entropy that allows for the formation of systems that can evolve and can reach new degrees of complexity and can reach also new degrees of freedom. And in principle, they would be unforeseeable. They couldn't be predicted from the Big Bang. Okay, nobody could have predicted the emergence of life on Earth with the numbers of the Big Bang. So it seems that there are more causes, there's more causal structure in the universe that simply fundamental interactions and fundamental particles. So let's move on to the third part of my talk, and I would like to talk a little bit about quantum mechanics and why I think that this is also a hint regarding the special universe that we inhabit. I'll try not be too technical, as I said, but probably you've heard about the measurement problem in quantum mechanics. So what is this measurement problem? Well, the problem with quantum mechanics is that we live with a dualistic formalism. So on the one hand, you have the evolution of wave function. This is the Schrödinger's equation. Here the important quantity is psi, the wave function, even though nobody exactly knows what this psi is. So there is a huge controversy regarding the ontology of the wave function. So the quantum mechanics is really weird because in classical physics, in classical mechanics, we are accustomed to deal with magnitudes that have a direct representation in the world. So we speak about space, velocity, mass, time, etc., and so on and so forth. However, this psi is crucial in order to retrieve, to get some prediction for nature, even though this psi doesn't give us directly any observable. So what happens is that when we perform a measurement, so we actualize, we update this possible solution of the wave function of the Schrödinger equation, and only one of them gets real. Only one of them, the one that gives us precisely the result of our experiment, is updated, is actualized. So there is the Born rule explaining the probabilities of updating one of the possibilities. But my point is that we seem to live in a universe with, at the fundamental level, we are having two very different processes. Again, this picture is due to Roger Penrose. So we live in a universe where if you are not performing any measurement, so nature behaves deterministically following this Schrödinger equation. However, when we perform a measurement, when we obtain information, then we have this reduction, this wave function collapse, that it's not a deterministic process, it's a statistical process, it's basically random. So, of course, very few physicists are happy with this picture. If just because, well, you may think, what is special about a measurement? So if you are, especially if you are materialistic or you have a deterministic view of the universe, so you would say, okay, but a measurement is not fundamentally different from any other physical process. So why, when I perform a measurement, I have to change my description from this deterministic evolution to this random, to this jump in the wave function, that it goes beyond my equation. It is random, it follows probabilistic rules. Why is that? Well, that's a very good question. And the point is we don't have an answer for that. Take home message, we don't have an answer to a measurement problem, one of the biggest theoretical problems in quantum mechanics. So, of course, it means that we don't know how this transition from the quantum world to the classical world is done. We don't even know what is the border, where should we put the border within the quantum strange world of superposition of wave function, where matter behaves like a wave, and the classical world where we have particles with definite positions and velocities and so on and so forth. It's poor Niels Bohr in this border that nobody knows exactly where it is. Probably the most notorious example of this conundrum between the quantum world and the classical world is the Schrödinger's cat, this Gedanken experiment initially. So the idea is that if there is a fundamental distinction between a Schrödinger equation and a measurement process, that imagine that I have a box, a closed box and a cat within the box, and I have here some device, and depending on here, this is some radioactive material, and depending on the decay or not decay of this material, then there is some device that triggers a hammer, and the hammer hits a vial with poisonous gas. So the gas is released depending on the random decay of this material, of this radioactive material. So according to the interpretation of quantum mechanics, so we would have a superposition, so all these possibilities of the cat being dead and being alive until the very moment in which you open the door, you open the box. So once somebody opens the door, so all these possibilities are actualized, are updated into a dead or an alive cat. So hopefully an alive cat. So this is really weird, and this is very, very uncomfortable for many physicists, and comprehensively so. It's well, but I think it's relevant for our discussion because it shows how there are some mysteries in nature that we don't master. So nature is probably weirder than we could think. There are some attempts to solve this problem. One of these attempts is referring to the coherence that, of course, I cannot go into the details, but the idea is, since in the classical world, we are dealing with many, many degrees of freedom, so we have many, many other particles, and so we are not in the microscopic level. So in the interaction with many other particles, all these weird superpositions of dead and alive cat, physically, they don't make sense. So if this is the initial situation where I have four possibilities of dead and dead cat, live and live cat, dead and alive and dead cat, it's a 2x2 matrix. So with environment-induced decoherence, the strange possibilities of dead and alive and dead cat, so they shrink, they disappear, and I would end up only with the two classical possibilities of alive or dead cat. So this is a very interesting program, and of course the coherence is something that we know that happens. So the coherence is the main problem that we have to develop quantum computers, because so the coherence is lurking behind all these quantum processes, and it seems that it turns everything classical. But from a fundamental point of view, the coherence in itself doesn't explain the measuring problem, doesn't explain the appearance, the emergence of definite outcomes. And even what is more problematic, it doesn't explain that we experience the world the way we do it. So why we see the cat or the classical objects in specific positions and not like waves? Could be another possibility that we experience the world like waves. That's one of the possibilities that it's allowed by quantum mechanics. But so we experience the world in a classical way. So let me go a bit into this problem, because I think it's interesting for our discussion. So this is a very basic schema for a measurement. This is known as a von Neumann schema of measurement. I have a system in state Si, and I have some device and apparatus that it's ready to measure the system. And if everything works properly, there's interaction, then this apparatus, this device is able to point at some line marking I, saying that the system is in state Si. Okay, this can be expressed mathematically with this evolution. So the idea is that I can always do this in quantum mechanics, and I can avoid, if this is a good device, I can avoid the strange interference terms, the IJ terms. So I only have here terms that are with the same subindex I. It's just telling me that the device is going to measure, it's going to be in a state AI, showing that the system is in state Si. Okay, but this is something for the time being, it's only formal. So I'm not saying exactly physically what these magnitudes are. So am I referring to position, to spin, to velocity, to what am I referring? So that depends on the specific measurement that I'm performing. Now, if I take let's go to the extreme, to the situation in which the observer is involved. So I have my system and my device, and I also have some observer that will be in a physical state OI. And if everything goes smooth, then I will keep this perfect correlation between state Si, so the system, the apparatus in the pointer state AI, and the observer in the state OI. So all of them are saying that, okay, I'm able to say that the system is in state Si. But again, we don't have any clue about the physical meaning of this state. So this is just the formal, the mathematical formalism of quantum mechanics. So we need some interpretation for these quantities. So what are these magnitudes? Now, there's an so-called existential interpretation by Wojtek Zurek. And Wojtek Zurek explains that, so I think it's really worth to listen to his words, because he poses a very, very important question. Why the preferred basis of neurons, so my physical state as an observer, is correlated with the familiar quantities that we see in the universe? So I need an explanation for that, because I don't have in the formalism an explanation for that. If I were dealing with classical physics, I would have an explanation, because the symbols have a direct interpretation with my measurements. But remember that I have here something that is not directly observable. So I need an interpretation. So his interpretation is that, well, evolution can explain that. So, and the reason is that our senses evolved to gain information about the world. So to refer to those magnitudes that are more stable. So we evolved to gain predictability. In as much as we can predict the behavior of the world, then we survive, and that's why we measure the things that are more classical, because are the most predictable. So as you see, the final quote is, classical reality can be regarded as synonymous with predictability. So that's his interpretation. Now, there's a confusion here, and I call this the epistemic confusion. And the confusion is this, that if I'm referring to the physical state of the observable, so that would be something like the neural correlates of vision. So this is the visual cortex, but this is different from the observer experiencing or knowing that the system of interest is in state Si. In other words, in the formalism, when I'm writing down OI, I'm referring to a physical state that by definition is different from what I would call in current jargon qualia, my experience of seeing that the system is in state Si. So neurons, state of neurons are not directly the same that perceiving that the system is in state Si. And because of that, it makes no sense in the formalism refer to classicality or predictability, because in the formalism, those are meanings that have no sense in the formalism. The founding fathers of quantum mechanics, Werner Heisenberg, saw this point very clearly, and he, with Niels Bohr, explained that we need classical physics to make head or tails of quantum mechanics. To interpret quantum mechanics, we need the language of classical physics, or if you wish, of natural science. And he said this for the very reason that if I wish to interpret the formalism of quantum mechanics, and the formalism of quantum mechanics is necessary to describe the universe, I still need to refer to my observation. So observation, classical observation, are a key ingredient to make sense of the quantum formalism. So this is a very, very interesting point, because it's telling us that our most basic description of nature doesn't work without the information that comes from upper levels, like the levels in which human beings perform observations, perform measurements. So quite interesting point. So I think that I still have like 10 minutes. This is the last part of my talk, and I would like to spend some time talking about the symbol grounding problem and the question of information, and whether it is possible or not naturalize information. So of course, so it's a huge topic, question of information. There are many books on information, and we live in the infosphere. So if I might recommend this book by Luciano Floridi of Oxford University, The Philosophy of Information, and he makes a nice distinction for different kinds of information, what accounts for information and what doesn't account for information. For instance, he distinguishes between relevant semantic information that makes knowledge. So not all information is knowledge. Knowledge needs relevant semantic information. He speaks about human beings as those organisms that can develop a growing knowledge of reality, quite relevant. So there's a growing knowledge of reality. So somehow information, relevant information, increases with human beings. And his definition of reality that is of less interest here. But the question, the important question here is the symbol grounding problem. My point is, so it seems that information needs some material basis, but on the other hand, as human beings, we are able to communicate using symbols, using language, where this material basis can be moved, can be changed at will. So for instance, we have different languages, so we are able to translate in different languages, but we can refer to a tree with different words, but we all have this idea of tree. Now, Luciano Floridi tries to explain how this symbolic language could have emerged in nature, or could emerge in artificial intelligence, just because of communication between different devices. And of course, we need to start from what is called the zero semantic condition, that of course it is that no external programmer introduces surreptitiously this language, because that would be cheating. So the language should emerge from the machine or the artificial intelligence or the system itself. So his idea is that imagine that I have some machine, some system that interacts with the environment at some level of abstraction, LOA1. So imagine that it hits the wall, and then this machine turns right every time it hits the wall. Then the output turning right is a function of the environment. Now we could have a second machine in a different level of abstraction, LOA2, where all these inputs now are the outputs of the initial machine. So turning right is associated with some symbol that are available in a reservoir of symbols in this machine too. So I would have a different mapping, not only a function of the environment, but for every internal state of the machine, I could associate some symbol. So that's what this second machine does. And now if I combine two of them, I could have this working machine with two parts, one of them creating these internal states in its interaction with the environment, and the second part that properly creates language, creates symbols, and associating symbols to each one of its internal states and interaction with the environment. Now, does this work? Is this a way of naturalizing information? Well, I think that there are many unclear things in all this schema. For instance, well, this division of machine 1 and machine 2 that somehow is done by human beings. It's very unclear that this happens in a machine, that this could happen in a machine. But more importantly, so there's a translation of internal states into symbols, but also of internal states in its interaction with the environment. So I should have some criterion to translate from an environment that usually is analog, many different possibilities, and in a continuum of possibilities, to internal states that are discrete. So that I will have a different language, so digital language where I do not have the continuum that mimics the environment. So what are the rules for that translation? That's very unclear. So the point, and I think that I would like to stress this, is that so we deal with information in nature, but we human beings deal with information in a different way. So let me explain in the last part, in the last minutes of my talk, what I think is the last complexity in nature, and it's the emergence, what I would like to call the emergence of immaterial or intellectual knowledge. So this is quite classical in a sense. My point is that we can see this from an evolutionary perspective. Now, in evolution, there are two basic concepts that are key for the success of the system that is evolving, and it's persistence and adaptability. So persistence has to do with the identity, the capacity to keep its own identity. Otherwise, if we lose our identity, it makes no sense speaking about evolution, because what does evolve? The whole universe. But on the other hand, in order to keep the identity, you need to interact with the environment and being able to change a bit. So to have some plasticity, to adapt to the environment, to find the right place where you can flourish as a living system. Now, my thesis is the greatest possible plasticity is that of immaterial knowledge. So we deal with information in a very peculiar way, because we are able to constantly redefine context. So we are not stuck with a context, so we are able to see new information. So we are able to find out how can I solve this problem in a different way with creativity. It's something very human. So it seems that in all this flux of information and in all this adaptation, these processes, this is an idea by Professor Gianfranco Basti. So there could be some sort of closure. He calls it a transcendent closure in this hierarchy of information. And now information is able to lift off from matter. So it's like the taking off from matter of information. So that's what we call immaterial or intellectual knowledge. So we're able to abstract, so to take forms and somehow to get rid of matter, of the embedment of forms in matter, in nature, and get to know forms immaterially. So in this intellectual knowledge. This is the classic definition of knowledge, this immaterial possession of forms of information in this case. So I think that here there would be also material for future research. So if we want to understand the emergence of man, of human being from nature, compatible with God's action, and I think that we should understand better these processes of self-organization of nature, this increasing complexity of nature, of course, how information itself seems to organize in hierarchical ways. This is a field where biology, theoretical biology is really improving, as it's reaching very, very nice results, this hierarchical structure of information in living beings. The emergence of language, the emergence in the history of nature, of the human being. Well, how does language emerge? How this capacity of symbolization emerges? So this is a good question to understand this singularity or speciality of exceptionality of human being in nature. And I think that it would be also very, very worth it to understand, well, how can we have a system like human beings that are able to make discoveries, but also to create new problems or new solutions to old problems. There's a very beautiful book by David Deutsch. It's titled The Beginning of Infinity, and he simply says this idea that once knowledge emerges in nature, material knowledge, then infinity is reached, because we are able to, well, to do many things that make us, in some sense, independent of our environment. Okay. It seems that we've gone perhaps too far from the title. We've moved away from the title, but I would like to recap now and say that, in my opinion, all these singular situation of the universe, of systems, of the description of nature and the emergence of information, of symbols, especially symbols, I think that all these singularities are pointing towards the big singularity. It's a creation or personal God. Why is that? Well, I think that we live in a universe where epistemology and ontology are really intertwined. So we have some epistemic organism in the ontology of the world, but we also have in all this epistemic structure of the human being some references to really extant systems. So to ontology is not just like our thinking in the void. Or if you wish, I think this is also a beautiful picture by Roger Penrose explaining or representing the mystery of the three worlds. He's kind of Platonic, and he speaks about this physical world. Part of it gives rise to brains, to human beings that enable these mental features, this possibility of thinking, of intellectual knowledge. And part of this intellectual knowledge is able to build up mathematics, and part of mathematics is able to deal with or explain the physical world. So, this picture doesn't hold in itself. So it's not self-sustaining. So there's something really weird in our universe when all these things can happen. So I would like to end with two quotations, and I think that what I'm pointing at in the end of the day is to the question of the universe, our singular universe, our exceptional universe, but the biggest singularity of all perhaps is that we are able to understand the universe, what is called the intelligibility of the universe. Now, two very smart guys, two very smart people have thought about this intelligibility of the universe. In a letter to Maurice Solovin, Albert Einstein explained this comprehensibility of the world as a mystery. He spoke about the miracle. the success of such a project, the project of science, presupposes this ordering of the objective world that could not be expected a priori. So why are we entitled to expect this intelligibility of the world? And well, in the end of this beautiful quote, he says that this is just a miracle, and we must be satisfied to acknowledge the miracle, but there is no way forward without there being any legitimate way for us to approach it, this miracle. Now, compare this quotation with this quote by former Pope Benedict XVI, when he speaks about mathematics, about the correspondence between mathematics, science, and the real structure of the universe. And of course, the former Pope also had this feeling of awe and of being in a wonderful universe. And there is a profound correspondence. But then there is this inevitable question, whether there might be a single original intelligence as a source of these two different kinds of intelligence, our subjective intelligence and the objective intelligence or ordering of the world. And in his case, this reflection on the development of science brings us towards the creator logos. So these different answers to this big singularity, the liberty of the universe, that of course is no other thing than the leap of faith. So of course we cannot overcome this leap of faith, but I think it is worth to show how these two very smart guys answer to this singularity, exceptionality of our universe. I think I've spoken for more than 45 minutes. I will stop here and I will listen to your questions with my utmost attention. So thanks a lot for your patience and your attention.
Thank you very much, Father Javier. So yes, we are a little bit late, but I believe we have still time to ask at least two questions. The first one of them comes from Pierre Naramini. I hope I'm not wrong in pronunciation of your name, Pierre. So please unmute yourself, Pierre, and ask the question.
Thank you for your lecture. I wanted to ask, is the problem of measurement limited to quantum scales? Does it have any consequences to macro level measurements? That was my question. Thank you.
It's a good question. The short answer is we don't know. So there are different proposals to investigate what are the limits of quantum superposition. And so the point is that we are increasingly able to have interference or superpositions of bigger and bigger molecules. As far as I know, I think that we are able to have superposition of molecules with 60 atoms. So it seems that we are approaching the macroscopic level. So one question is, what's the threshold at which classicality appears? So in somehow quantum mechanics is violated. So we don't know. So we don't even know whether we are asking the right question. So because one possibility is that everything is somehow quantum, and so classicality is only like a shadow, like interpretation of the quantum level at a different scale. So this is a very controversial issue, and there is current research on it, but we don't have an answer for this specific transition from the quantum to the classical, and an answer to the measurement problem.
Okay, thank you. So the second question comes from Luca Settimo. Please, Luca, unmute yourself and ask the question.
Yes, thank you so much for your presentation. I was interested in the last part when you spoke about the role of information. I was wondering whether you can spend a little bit some extra words to explain what is so special of human being compared to non-human being, in the sense that I see sometimes a continuity there, for example, with the notion of intentionality and agency. Also, an animal will try to give meaning around itself to search for food. Of course, we have higher ability, but somehow I can see a continuity there. And I'm wondering about what you think about the information in that, let's say, threshold between human and non-human. Thank you.
Right. I thank you for raising this question, and especially the word continuity, because I think that the challenge that as believers we are confronting is how should we explain the continuity of the human being in nature. So we come from evolution, and that's it. And I don't need to invoke some I don't know how to call it, supernatural forces or whatever to explain the emergence of the human being. So there's this continuity, but at the same time we're talking of a true apex in nature. I think that it's an apex, so it's continuity and discontinuity. And I agree with you on the idea that so these goal-directed activities or intentions are somehow present. Well, perhaps they are present in a proto form in non-living nature, but of course it's present in animals, and of course in bigger animals. So I think there's these goal-directed activities, there are intentions. I think the way how I would understand this transition from continuity to discontinuity is this question of immateriality. So in my view, in the human being, what we are reaching is the point at which information can be dealt with without specific matter. So matter, of course, we still need matter, we still need neurons, we still the brain, the processing. But my point is that so this information doesn't have to be stuck to this piece of matter. So it's like I would like to talk about the lift off of immateriality. And in my view, that's the apex that is reached with a human being in nature.
Thank you.
Thank you very much. Well, I myself have several questions, but I will let myself ask just one, and then maybe I will ask you, Father Javier, to stay a little bit longer after we end the official part. But the last question, it will come from me, and it will refer to the emergence theory. So how do you think, what justifies us from the scientific point of view, and maybe philosophy of science point of view, to claim that emergent structures are not epistemologically emergent, but ontologically emergent?
Okay, yeah, a very good question. So it's, I would say, I think it is right to pose the question looking at the scientific description and saying, okay, what am I able to do with this? And what we know for sure is that so with our basic description, with our laws, and with our fundamental particles, whatever they are, we don't know whether quarks and leptons are the fundamental particles. We don't know. There are many things that we don't know, but imagine that we have the fundamental particles and the fundamental laws. So the question is that such procedure still underdetermines what's going on in nature. So we need to add information. And usually what we need to do is to introduce boundary conditions, or we need to introduce more information ad hoc to explain or to provide a reason why this specific process is updating nature within all the possibilities that the scientific description is offering me. So in science, we are continually dealing with this information updating through boundary conditions, through recourse to symmetry breaking, for instance. That's now current physics works in the framework of symmetries, but at the end of the day, so symmetries are very good in order to provide a framework where everything more or less fits. But at the end of the day, I need to speak about symmetry breaking, because so particles are real, and there are symmetries that are broken in nature, for instance, in weak interaction. So my point is that we always need to introduce a different level of description in our basic theories in order to describe a system, a process, or whatever. In my view, that's a strong indication that emergence is truly ontological, that there's real novelty, because we don't know what are the degrees of freedom of the universe. So we come to know degrees of freedom as they update themselves, as they appear.
Mm-hmm. Okay, thank you very much. It is an interesting answer. Once again, thank you for the lecture. I would like to thank all the participants, those who listened to us tonight. And one last time, I would like to remind you that the next lecture in our series will take place on 16th of February, and it will be delivered by Dr. Brian Green from Santa Clara University. And the title of the next lecture is Big Questions and a Few Answers at the Intersection of Artificial Intelligence and Religion. So please feel invited, and thank you for being with us tonight.